Here we're going to look at chemical bonding and specifically look at electronegativity. So our learning intention is to recognise different electronegativity in elements and polarity in bonds. So to begin, it's important to go over a definition of electronegativity, and electronegativity is the relative attraction that an atom in a molecule has for the shared pair of electrons in a covalent bond, and that definition needs to be known word for word in order to obtain full marks in an exam. Now, a covalent bond between two identical atoms, the pair of electrons there will be shared equally once the atoms are identical, but if you have bonds with different atoms, the pair of electrons will be more attracted to one atom than the other, and this is the whole concept that electronegativity is based on. So when looking at electronegativity, it's important to look at the scientist called Pauling. And Pauling studied the amount of energy needed to break up certain bonds. And what he found was that chlorine had 4 times the electron pulling power, or electronegativity as we now know it as, of calcium. Developing on this idea of Pauling, it was discovered that electronegative elements are actually the very reactive nonmetals, such as chlorine, fluorine, bromine, and iodine, where the least electronegative elements are the reactive metals of potassium, sodium, lithium, and rubidium. Elements with low electronegativity values then are said to be called electropositive. Electronegativity values are very useful, and the main ways that we will look at electronegativity values is to predict polarity in covalent bonds and to predict whether compounds are ionic or covalent. So before going any further and predicting polarity of covalent bonds, we must look at what it means to be a polar covalent bond. So the definition for a polar covalent bond is a bond in which there is unequal sharing of electrons, which causes one end of the bond to be slightly positive in charge and the other end to have a slightly negative charge. And this is very evident in a bond of HCl, or hydrogen chloride. If we're to look at the structure of hydrogen chloride, we know that we have hydrogen bonded to chlorine. Now, we know that chlorine is extremely electronegative, so that means that the electrons will spend a longer time in the bond down near the chlorine than they do at the hydrogen, which gives the hydrogen a slightly positive charge and the chlorine a slightly negative charge. So we would call this a polar covalent bond because there is an unequal sharing of electrons. The opposite of a polar covalent bond then is a pure covalent bond, and a pure covalent bond is used to refer to a covalent bond where electrons are equally shared, and that would happen in molecules with the same atoms present, such as oxygen, hydrogen, etc. So, when predicting polarity of covalent bonds, we must assign electronegativity values to each of the atoms in our molecule, and the greater the difference in electronegativity, the more polar the bond. So, most molecules that have polar covalent bonds, the molecules must be polar themselves. So, if we take a look at water, we can see that the hydrogen has an electronegativity value of 2.2 and the oxygen has an electronegativity value of 3.44. So when we get the difference between the two of these, we see that it's 1.24, and a value of 1.24 indicates that the molecule is bonding is highly polar covalent. If we look at hydrogen chloride, we see an electronegativity difference of 0.96, and that's gotten from subtracting the 3.16 and the 2.22 to get a polar covalent bonding. If we look at methane, we see the 2.55 and the 2.2 are subtracted to give an electronegativity difference of 0.35, which makes it a negligible polar covalent bond. But in hydrogen, where both of our atoms in the molecule are the same, they have the same electronegativity value, so their electronegativity difference is 0, and that makes the bond pure covalent. Now, you may wonder where we got these values and where we figured out whether something was covalent or not. So these electronegativity values are in the log tables on the periodic table, and these labels that we assign them, we will discuss this in greater detail in a few minutes. So it's important to note that some molecules are not polar, even though they contain polar covalent bonds. Now, usually these molecules will be symmetric, and as we can see here by the examples that I've done out, CO2, BCl3 and CCl4, they are non-polar molecules, but they do have polar covalent bonds, and they're non-polar because of their symmetry. So there's an easy way to determine whether a liquid is polar or non-polar, and the easiest way to do that is to look at the effect of a negatively charged plastic rod on a stream of liquid that is flowing from the burette. So if the liquid is polar, for example water, the stream of liquid will be attracted to the rod, and this is because the positive poles of your polar liquid will be attracted to the negative rod. Now, it's important to know that if we replace the negatively charged rod with a positive one, the water molecules will still be attracted to the positively charged rod because they will turn so that the negative poles in the water molecule will be attracted to the positive rod. If we were to complete this with a non-polar solvent such as cyclohexane, no attraction would be observed since there is no polar molecules in the liquid. So one of the most important properties of water is that it is an excellent solvent, and this property depends on the fact that water is a polar molecule. So it's found that most ionic substances and most polar covalent substances dissolve in water. So an example of an ionic substance that can dissolve in water is sodium chloride. And this happens because the ionic bonding in sodium chloride is overcome by the strong attraction between the ions and the polar water molecules. So these ions are dragged away from the crystal lattice of the sodium chloride and surrounded by water molecules, which causes them to dissolve. So another way that we can use electronegativity values is to predict if compounds are ionic or covalent. So we would say that a compound that mainly has ionic bonding would have an electronegativity difference of greater than 1.7. We would then be able to say that a covalently bonded compound will have an electronegativity difference of less than or equal to 1.7. An electronegativity difference between 0.4 and 1.7 would indicate a polar covalent bond is present, while a non-polar compound will have an electronegativity difference of less than or equal to 0.4. This could also be called a pure covalent compound. So here's just a few examples, and we've met these ones already: our water, our hydrogen chloride, our methane and our hydrogen. So hopefully now you can understand why the electronegativity difference explains why water is highly polar covalent, why hydrogen chloride would be polar covalent, that methane would have a negligible polar covalent bond, and that hydrogen molecules have a pure covalent bond. It's important to look at ones then that are ionic as well, and potassium fluoride will have an electronegativity difference of 3.16, and that's greater than 1.7, so that makes it an ionic compound. Now, it's important to note that these are not definite laws, they only act as a guide, and that exceptions include lithium hydride, sodium hydride, potassium hydride and calcium hydride. So that's it for this video. Have a read over the learning intention to make sure you understand everything we've gone through.